Is anybody there? Okay, so Will and Mule and Julie, is everybody? All right, so I just hit the record button, so I should be able to load this up a little bit later on. Um, so how this works, if you haven't joined in, is you can try to see if your microphone will work, but if you do that, then I ask you to kind of mute it if you're not talking because you get some feedback going. You can also just chat problems or questions rather right down in the screen. So do you guys all have that first problem up on the screen? Can you see that? Okay, super. And then I've got just a bunch of the different figures up there loaded, and we can also talk about other problems or things if you want as well. So who's got a question? Okay, so let's see here. Number 3 is going to be, let's see, that's number 2. So that's the kind of this ASDD one, is that right? Okay, so did you have specific questions on it? And we talked a little bit about it, right, in class. So, you know, what I like to do is think about kind of what's the base rotation, and then you kind of move outwards, right? So, what's kind of the base thing that's going on? Do you know what I mean by the base? Kind of really, what's the first thing? What's the first big driver motor kind of going? Yeah, so we got the omega planetary, right? So really, if I want to do the overall omega, I'm going to start out with the omega plan, right? And then you guys have to kind of, you know, you could just set up your own coordinate system, right? So that part's up to you. You just want to make sure it's a right-handed system. Okay, then what's the next kind of motor, the next one out, right? So that whole base is that's going with the planetary, right? The whole thing's going around there, and really that base you could sort of combine and look at, you know, really this whole structure is what's going around with that planetary, right? Then what's the next motor that's causing some sort of motion? Yeah, so now we can add in this W yaw. Okay, and so that's this motor right here that's on the base. Okay, so you know what we're going to do next, of course, remember, is you're going to have to start thinking about the angular accelerations. Right, so let's look at it for a second. Could the planetary be increasing its speed sort of in magnitude? Or I'm sorry, I got to remember if I had said they were constant or not. Let's see. Yeah, we did. Sorry. Okay, so then does that planetary spin ever change directions? No, because it's always just pointing straight up. Okay, so then let's look at the yaw one. Okay, does that yaw ever change direction? Okay, so which direction is pointing straight up right now? What could make it change direction? Yeah, the omega planetary is the only thing that could possibly make it change direction. So which direction is a planetary one? It's just straight up, right? And so if you've set your K going up, that's fine. Oh, I guess we do have some axes on there, right? So if depending on what you want to use, I drew, you know, there's some little XYZs on there as well. So depending on what you want to do, you could also sort of follow that, right? And so we could do like, then this would be capital C, right? This would be our capital X, and then this would be our capital Y. Okay, so yeah, so that's always going to point in that J, right? In which direction does the omega yaw point? So it's J as well. So maybe that could make it change, right? It has that potential. But to find out how it changes direction, I would just do a J cross a J. Okay, so does the yaw ever change direction? No, they're just all adding up. Those two are going to just actually combine. Like you could have what that thing was for, why that axis was there is because it sometimes could help you do what we call counter rotation, and it just helped with some of the simulations of what we were trying to get the pilots to feel. So what it could sometimes do is I could almost make it always face sort of like this wall, and I was doing that in one of the class sections. But basically, if I rotated the planetary in that positive direction like you see, and I rotated the yaw in the exact negative, then the person wouldn't feel like they're spinning at all, right? So you could give them some G's, but basically they'd always be facing the wall, so they wouldn't end up having any change in their angle at all. So the omega yaw does not end up changing direction at all. Julia, does that make okay sense to you? Because they're just both pointing up. Okay, good. Any other questions on the yaw part then, the planetary and the yaw?
Do we still need to use the transformation matrix to transfer the yaw omega into the original X, Y, and Z?
Yeah, you would. It would depend on which one we were going to ask you for, and we actually didn't. We didn't ask you to put the transformation matrices in there. But yeah, depending on which one you would want it in, right? But you could just add the planetary and the yaw together in the end, and then you could use whatever the angle is there to transpose or to transform that yaw and planetary back into the cab coordinate system, because that's when you're going to want, like we talked about before, you'd want it in the person's head, but really you can just add the planetary and the yaw together.
Well, if we wanted to solve in terms of the X, Y, and Z, like the original one from the planetary axis, are we allowed to answer it like that, or we only have to do it in terms of the actual module?
No, you can choose to, you can say, I'm going to put it in such and such a coordinate system, right? Because I don't think let me just double check and make sure, because I don't think I asked you find an expression for the angular velocity of the gondola and the angular acceleration for that position shown, right? So you can do it in any one of those coordinates you want, right? You can express it in any system you want. It makes the most sense to do it in the little XYZ because that's what the person's going to say. But do you remember me? I'd kind of point to one direction, and I said, it doesn't really matter in the end what coordinate system you're talking about this vector, as long as you tell me which one it is. Do you understand that or not?
Yeah, no, that makes sense. I just like to do it in the big X, Y, and Z. I think that's what I'm going to do.
Okay, yep, that's fine. You just have to communicate that. Okay, but I would also do, you still need to set up all your coordinate systems, right? Say, kind of say what they're attached to. And then just at the end, you should get in the habit of writing them in the right and the correct unit vectors. You know what I mean? Like if you're going to do the roll, then you might use, say, the little x, but the little x isn't necessarily going to always be the big X.
Yeah, I understand that. And then I would just transfer that into the big X.
Yeah. Okay, so we also had a question where Long is saying, you have the pitch in changing the yaw's direction, but that gimbal, if you look on where that is, the motor for this yaw axis is always right here where I've drawn that big arrow, right? It's always rotating there and it's always pointing upwards. And then the next one that would come about is and let me keep going there, Long, and then see if that'll make sense in a second. So then what's the next rotation that's going on, right? So we started from in the beginning and then we're going out another one, right? And then it's going to roll. Okay, so now this thing is going to roll. Okay, all right, good, Long. So so the roll, right, isn't going to change this axis here physically, right? Okay. But the roll was facing this way, right? And then once what are the planetary and the yaw going to make it do? It'll make it change direction. Does that make sense to you? So if it's, I guess I'm going to do like a little top view. So if I was looking down, if I was I'm trying to remember how I do that. What do I draw? Like kind of like that, right? Don't people do? I don't remember. So I'm just looking down, and basically, if I'm looking, actually, let me do like this will be better, right? So I was pointing this way. So if that's my omega roll from the top one, right, then the planetary is going to make you do like this, right? So it's actually going to change the direction. So the omega plan, if I'm looking from a top view, right, so this is a top view, right? So the omega plan plus the omega yaw is going to make that roll axis change. Okay, and then what's my next one? Yep, so that's going to be my pitch. Okay, and you just have to figure out which one of those are all the right, X, Y, and Z. You also need to attach your coordinate systems to different gimbals and say how they're rotating, and then express the omegas all in the, in the correct axes that are always true. Okay, and what's making the pitch change direction? Everything, right? So I get it, but if I'm looking at the top again, right, then this is the omega pitch, right, at that instant, right, and it's gonna be changing due to the planetary and the yaw. But then if I look at like a front view, right, so if I look at a front view, where now I'm looking at it, down this axis, right? So if I'm looking at it this way, then the front view, I'm going to have. Oh no, then I won't see. Oh yeah, well, I'll see the pitch. So if I look at the front view there, right, then the pitch is coming out that way, and then the roll, right. So this would be like the omega pitch of it coming out the side, okay, and then the roll can make it go up like this or down, and it also still has this top one like we talked about before. Okay, are there questions about that? Will, was that you who asked about that? Okay, does that clear things up or not really? Okay, so, one thing you can think about how these go is just kind of write what's the, how is it moving, what's the first thing. So we had this one was the first thing, this is the second, that's the next outermost gimbal or motor, and that's the last one. So really, the last one here is affected by all of the things before it. Right, so you just kind of group them together, and in this case, you still want to do, if you're figuring out the angular acceleration for the omega yaw, you still want to see if the planetary would affect it, because it could, but it's just in this case those two are in the exact same direction, so it does not end up affecting the direction of the yaw, because it's just like a y cross y. Yeah, so let's look at the roll, right? What makes the roll change direction? Let me go down one, the yaw and the planetary, right? So when we do those, then, right, all we have to do for that part is like that whole Q thing that we did, right? So if we look at the time derivative of a vector, and we just want the absolute, right, in a non-rotating frame, then we do the Q dot in the local frame, which was that, whatever we call it for that role, and we said that was 0 because it's got constant omegas, right? And then we're going to do kind of whatever's making it change direction, right, crossed into whatever the Q is. So what that means is I've got omega planetary and the omega of the yaw. Those are both going to make, right, that's essentially what this guy is. And then the Q here is just the omega of the roll. I'm sorry, that should not be a plus. Let me find out where my little eraser thing. Which should that be? Cross. Okay. And that's going to give you the change in direction of the omega roll. Does that help, Will? You do basically the same thing for each of the different ones. Right, so that's how we figure out the change in direction, is just by whatever is making it go. Well, you just got to add all of them now, right? So because really what you're doing, I'm going to go back up to the next page, right? So really when you're going to take the time derivative, you're going to say, okay, I got to look at the plan. Does that change amplitude, right? Is it changing its magnitude? And we said, no, it's constant. And then you say, does it change direction? Right, so we add those two terms, which in this case were 0. Then I look at the omega yaw, and I say, well, that's going to have, is that going to have a change in amplitude? And we said, no, they're all constant. Does that have a change in direction? Well, if we did the exact same thing, I'm going to go to the next page. If I did this exact same type of thing with my cross product, I just ended up, remember, like we talked about before, where that's going to be a y cross a y, and that gives you 0, and that should make sense physically because the yaw direction is always pointing straight up, so it does not change direction. And well, really the overall omega dot, right? And then we just did the roll, okay? And then the last one is the omega pitch, right? So what makes the omega pitch change its direction? Yeah, everything. So you're going to add a term into right here, and then the only thing that's left for you guys to do now is figure out your ij's and k's, and then you need to do out the cross products. Yeah, give me a sec, Katie. So then for this part, for the as Ethan's asking about the omega and the alpha. Yeah, so set them up in the, like whatever your true frame is, like, maybe the roll is about the X, and then the yaw is about your U1, U2, or U3 or whatever, and the planetary is about your YN, and your yaw is about, you know what I mean? So do those. So set them up to something that's always true, and then just say at this instant in time, right? And then you can just make all of them, every X, every Y, every Z type of thing equal, and do out the cross products then. Okay, because you're going to need, when you do the project, like I was saying again, I think it's week 8 or 9, when you do that project, something like that, Megan. You may not need, you may only need, it's between 3 and 5, so it depends kind of on how you decide to set it up exactly, but because remember, go ahead.
Do we solve like all the omegas into one coordinate system and then do that equation for the omega, or for the angular velocity?
Yeah, that's what you're going to do in the end. So you're going to do them all just in their local one, like what we've done before. Don't you remember how we've done, like, maybe I'll say it's N in the capital Y, right? So here's what our capital omega is going to be, NY, and then I'll say it's plus P of U3. Right, we'd have something like that, and then I'd say, at this instant in time, those all line up, so that means that capital omega is also going to be like NU2 plus PU3, right? So now it's in the same system.
Okay, yeah, that makes sense.
Okay, good. Okay, any more questions with the ASDD one? So it's not too much different than what we did before, right? But we're just extending it a little bit. So the two things that are different is we have two in a row that are in the same direction. So that could be a little confusing for you, something challenging. And then the other thing is, I mean, this really isn't much different than that big old thing I did on the YouTube video, right? I mean, so that one we had on the YouTube video, didn't it have 3 different axes of rotation? It's pretty much the same deal. Okay, so there's a question about number 4, and there's 2 different parts there, right? So we had 4 and 5. So in this case, we've got O, A, and then B. So Katie, that's totally valid to do there as well. So if you wanted to go through that, that works just fine. So you can go O to A and then A to B. But you can also, you know, in this case, if we don't have, and if we've got the omega is only going around with the omega z, right? So that's just going with this one. Okay. Then what's going to happen is we're going to have some different things in our rel term, right? But it's actually okay. We can set up. Let's just say we were doing our velocity, right? And let's do our velocity. So let's say velocity of b is going to equal. Okay, and we said here we wanted to start it with O. So let's do velocity of O plus our capital omega crossed into R of B with respect to O, plus we've got some sort of VB rel term, okay, or we also call that R dot. Okay. So when we look at this one, right, we can say, well, first of all, what would happen physically if there was a V of O? What would be going on?
That would be like if the whole thing was moving, the whole crane.
Yeah, so we're driving the crane forward or backwards, but I think in here, right, it was not doing that. Okay. So that one's a 0. Does that make all right sense to you?
Yeah.
Okay, so then what have we defined our omega as?
Omega z.
Okay, so we've got this then being an omega z. Okay, and that's in what direction?
Positive k.
Okay, and you haven't quite said yet, right? We need to say how these things are going, right? But let's just say we've attached it, that XYZ, right, is rotating. How do you want to make that rotate?
So like x prime and y prime will rotate with omega z, and z prime will equal z.
Okay. Oh, I see what you're saying. Yeah. Okay. So then let's do a z, and we can just say z prime. So we'll do x, y, z like that, and then we'll just kind of put this here. Whoops, x prime. Okay. So then the primes are going to rotate with the kind of like with the cab, right? So that means it's omega z, like what you just said, and then we could set another one, you know, kind of down here that maybe we're going to use in the next one. And it's okay to put it here. You know, a lot of times I might actually put the axis so it was up along here, would make a little bit more sense, but for convenience we can do like this because it just makes our math a little bit easier at this instant in time. So you're going to call that, does that make sense then? Call that the double prime?
Yeah.
And then that's going to rotate with boom. Okay, so if that's my omega, right, in the first part, I'm just saying it's omega z, well, then what is my R from O to B?
It'd be 20I plus 34.6K.
Okay, so to do that, so like that's like, let's break it up just to make sure everybody is right. So because you're going 5 this way in the I hat, right, and then plus like a 40 cosine 60.
That was just A to B, not O to B, sorry.
Oh, okay. Did I do that? I think I did that all right. Okay. Does that make sense, everybody? So that's from O to B. Okay, so Ethan, what did you mean? Not J? Did it? Oh, yeah. Why did he say not J? Right, you guys see that? I was just kind of going at how our, I was thinking back to how what we're normally doing for these, right? Does everybody see that it's not J? Which should it be? Yeah, it's K. Thanks. All right, because our K's, we defined our Z as going up. This part's for 4, right? Because we've said our omega, right? For omega, we've defined that as being just the omega Z, right? So our capital omega, we said I'm attaching my axes just to the cab, and I'm going to center it at O and use O as the Führer point. So if I'm just sitting, right? So now I'm just kind of sitting, hanging out right here, right? And I'm looking, and I'm rotating with the cab. Does it look like B is going to have a relative velocity from how I'm rotating around? Yeah, so you could think about it like, one way you can think about it is if I stop my capital omega, which means I stop the cab, right? Then does point B still have a velocity relative to that frame, right? And it can still move back and forth, right? So that boom can still rotate back and forth. So that's what our VREL term is going to be. So how can I write that VREL term? And when I did this, I would probably put all these in a prime. I hadn't done my first one in the prime, but okay, because so that would be always true. Yep. So Katie's asking about the theta. Yeah. So how would you do that, Katie? Yeah. So we can do now our theta dot, right? So we can do this theta dot. And what direction is that in? Our minus, right? J prime. And we can now cross that into right. And in fact, sorry, these guys would actually be double primes now, right? When we measure the distance from A to B, those are better in the double prime. Okay, so now we're basically just going to have that's going to be 40 cosine 60 degrees, right, in the I double prime plus 40 sine 60 in the K double prime. And this is going to be my VREL term. So how am I going to use that in my acceleration? Will that have will that have to go somewhere in my acceleration equation? Yeah, right. That's going to go into the Coriolis part. Okay, and will I have any type of an AREL term? Yeah, and what things could my AREL include? Yep, I can have a centripetal and a tangential, right? Depending on what that theta dot's doing, right? Is the theta dot constant or do I have a theta double dot? It's constant, so that just means I'm not going to have a tangential one, but I am going to end up with an A-rel term that's got a normal component going right down the boom, right? So this my A-rel term, my like AB rel term for number 4 is going to be going down towards the center due to centripetal acceleration. Okay. I could even have, if this was a hook and ladder type of truck, right, then I could have an additional thing for a V-rel and an A-rel with the ladder extending. Okay, questions there? Yeah, so now you're going to have an omega total is going to have both of them, but also it moves your reference point, remember? So now the reference point is going to be at A instead of O. Yep, I agree with you that the omega total now, the capital omega of the reference frame I'm using, is going to equal omega 1 plus omega 2. Okay. Other questions about this one? Yeah, so Simon's now asking about the omega dot R, right, in the linkage one. So let me just double check. Are there any last questions on this one? Okay. So for the linkage, and we can do this with all of those. So the simple answer to your question, Simon, is yes. Okay, so you can always go through there, and I guess we had in one of the sections, I kind of started thinking about a different way to do it. Where what I did is I took my arm, right? So I'm always doing that, right? So I got my shoulder here, and if we say that's pinned, right, and then if I just did it like in the plane of the page, right? So this is pinned. And I said I went like this with my omega, right? Then which direction is the if this is A and this is B, right? Which direction is the velocity for point B there? Right, it's got to be tangential, right? So it's got to be perpendicular there somewhere. Okay, so it doesn't actually matter how I end up putting my frame, right? So I could put my frame some sort of weird three-dimensional type of thing, but if I look at the velocity of B, kind of with respect to this A, then it's still going to be perpendicular. Right? So it's still going to be the velocity of B with respect to A is still going to be perpendicular there. So the way that we end up expressing that mathematically, right? Because if all I had was the omega going down here, then it would just be, spiraling around like that, and point B would never move. So what you end up having there then is that omega of AB, right, dotted into R, and this could be either R of A with respect to B in this case, or B with respect to A. That's going to end up equaling 0. Right, so that dot product is going to end up equaling 0, and that's how we get the fourth equation that we need. Okay, does that answer your question, Simon? Aren't R and omega? Well, I guess that was my point there. The vector, if the vector R is, if those are parallel, then this would, that means that this thing would just be spinning like what I did right here. It would just be like, if you take your pencil and you twirl it between your fingers, right? And so essentially then you're never going to have any displacement between A and B. So they're not, if they're parallel, then you don't really have any motion. Okay? So they're absolutely not parallel. Okay, and then the others are just linkages that have different constraints, right? So this one has to move along this way. This one at that instant in time, right? If we've got the omega, which direction does A end up having to be in? Yeah. So I think this guy's going, if depending on, I can't remember if it's positive or negative, but that would end up kind of going up. Okay, and that Z, and you could even do that by saying, you know, that the velocity of A is equal to the velocity of this center point, right? Crossed into omega, the velocity of the center point plus this omega cross this R. Okay, and that'll give you whatever that amount is, 1.2 times the omega. Okay, any other questions on this one? Okay. I think someone just might have joined us and had your mic on. If you can mute it until you're asking a question, we get a little bit of feedback here sometimes. So the omega of AB could be in the IJK. Okay. I was trying to think of what the ink meant. The omega of AB, yeah, it could have, you know, at any given instant in time, it could have omega X, omega Y, and omega Z components. At some instances of time, stuff may stop, especially like here, it might be the farthest out instant at that immediate time shown. Do you know what I mean? It's kind of like top dead center in your in a crankshaft piston type of thing. So in all of these, sometimes you have to look at when things are out at a kind of one of the extreme points. Sometimes you get some zeros going on. But yeah, you want to write out your equations just saying that they're in the X, Y, and Z, and then see what happens. Okay, any other questions on this one? Yeah, so the four equations you're going to end up with there, well, is basically you're going to write something out like, you know, velocity of A equals the velocity of B plus, you know, you're going to have your I, J, K, and you're going to have whatever your omega X, omega Y, omega Z, and then you're going to have whatever your X, Y, Z position vectors are going to be. And so that gives you three equations when you break it down into I, J, K. And there's one post. There's actually have two example problems, and really three if you look at the second one in the book that's on this type of stuff. So the one we worked out in class that I did kind of quickly at the very end, I posted that full solution. There's a full solution one on the on that additional homework problem that we gave you, and then the fourth one is just going to be this. Right, so the fourth one, you just end up with like an omega X of whatever that times whatever your X distance is when you do the dot product, omega Y and whatever the Y, and then omega Z and whatever your Z distance is, and all that equals 0. So that's your fourth equation. Okay, more questions. Okay, so there's a question about for number 5. Sorry. No, for number excuse me, for number 5, you're going to want to use point A as your reference point. Okay, and that's what I do as well. Just, you know, there are ways if you have what we call in the end, if you have that kind of a single axis rotation where your two omegas line up, that there are ways you can do it, but it's going to, I think, get you into some danger once you start doing angular velocities and kinetic energies and things. So now you want to go to your reference point A first. Yeah, let's see what I'll do there. Yeah, what you would say there, so I had one question too about the crossing things. Excuse me for a second. What you do is you say at this instant in time. So, you can cross K prime and I double prime at this instant. If you didn't, if you didn't have that, you'd have to do the transformation. Right, so you'd have to transform I double prime into I, or vice versa, depending on which one you wanted. Okay, let me see if I can bring up the rotation. Okay, so sorry, like I say, don't know this one quite as well as some of the others. So how do I share something different? Okay, I'm going to get out of what we have right here for a second. And I'm going to see if I can open up a different one. No, that's not what I wanted. Hold on. Share screen. Okay, can you guys now see the matrices?
Yeah, I can see it.
Okay. So Ben, you had a question about it, right?
Yeah, so just have an annotate.
Yep.
Okay, so we'll take this one as an example. But if the z-axis is this way instead of on the other side, on the left, what do we do about the matrix down here? Do we change anything, or do we keep it it's still rotating this way, but just this axis is flipped?
Well, then
there a certain?
Yeah, I guess what I'd say is this B axis, is it rotated around the it still has to be about the positive x. So if you do your right hand rule, then B has to be rotated through a positive axis, and everything has to everything that we do is typically based on the right hand rule, right? That we have to have a right hand coordinate system. So if you had up here, so I'm going to draw, I think, what you're talking about. If I had a Z here, and I had and I guess here, this is from my German colleague. I grabbed his notes from this. So, and we had the Y here, right? That's what you're talking about, yeah?
Yeah. Yeah.
Okay. So then a positive, if you're going to use this transformation matrix you've circled, then it has to be, the B has to be now down like this, right? Because then, do you understand that or not quite? Because
yeah.
Because it's got to be a right-handed system. So to take care of that, all you have to do is, if it's going the other way, you just put a minus alpha in, right? If the B frame is rotated counterclockwise here, then you just use a minus 15 degrees instead of a plus 15 degrees.
Okay. All right. That makes sense.
Good. Okay, more questions. I may have to get back out and re-share the other page, depending on what people have questions about.
I have a question on number 1, problem 1.
Okay. Let me see if I can get out of here. Let me give two to see, because Will, you and Ben have both asked questions. Let me just see real quick if anybody who hasn't gotten to ask a question yet has a question. Hold on, let's see. Okay, so we'll do a quick look at 1, and then Will remind me about 6. All right, so that's here, but you guys aren't sharing. Let me see, I don't think I've shared it yet. Okay, so everybody see this one now? Okay, so go ahead. What do you guys have questions about?
So I got down to the point where I'm finding the velocity of point P, and I'm just a little confused on the v relative vector and how we find that and how we use it into that equation of finding VP.
Sure. So it depends on how you guys have both set this up, right? Because I think maybe Megan had a question about it too. So once you get to here, right, you've got to decide how are you going to set your coordinate frame up, right? So the big thing, you have to first of all define all the, the X, Y, and Z, and we've kind of done that for you. Although that the writing got a little confusing, I still don't know what the best thing. Some people in the office hours said they liked all the primes. I know those seem to get clunky to me or a little confusing. I don't know. I'll have to ask you guys towards the end and see. Maybe we'll have a vote. But the big thing is you also have to define what your capital omega. So what are you going to define everything with? Because if you look at the problems that we were just talking about with the kind of the crane, right? Then for part 5, for number 5, right, where it was attached out at the end, what are your V-rel and A-rel terms? That's for anybody. What are for number 5? Remember, we attached our frame out at the very end. So what were our A-rel and V-rel terms going to be? Let me show you the picture. All right, so for this guy, we're attaching our frame at the end. Right, so we're rotating not just around with the cab, but we're also rotating this way. Right, so if I'm out riding on the boom, so here I am hanging out on the boom, then does B look like it has any motion with respect to me? Right, so they are 0. Okay, so the rel terms of B with respect to A down here are going to go to 0 because I put them, there are 2 points on that same rigid body and my omega is going with that rigid body. So the rel terms for that one are going to be 0. Okay, so if I go back up, so if I head back up to this one, right, and if I end up saying that my capital omega, I'm going to attach to we've just been calling it propeller, so attached to the propeller, or PQ, right, then if I'm standing here, right, and I'm looking down at P, right, does it have a V rel term?
No.
No. But if I decide instead, so that's attaching my axes to the double primes, right, where the double primes are going around. If instead I attach my axis to the single primes, right, which is really just kind of riding around with this guy, right, and not spinning with omega 1, then will P-rel have a value?
Yeah.
Yeah, it'll be kind of like a tangent, right? So at this instant in time, it would be going like that. Okay, so if you're doing, most of the time I attach it out at the end because most of the time I want to know what that capital omega or the angular velocity of a body is anyways, right? So depending on what we've asked you to do, right? But here you would just say, well, via P, and what's your best kind of reference point to use?
Would it be A?
Yeah, so I almost always use, like you're saying, VA, and then I just move backwards. As I've said before, there are different approaches for using it, but I think this is going to be the best one once we get into the kinetics portions as well. Okay, so like we had said before with this, right? The rel term, if I've attached it like this, then that's going to go to 0. If you do attach it right to the other one, that's fine. You get the same answer. It just depends on where the terms pop in. Okay, so then for VA, right? So again, depending on which one you do, if you do the VREL, it's just going to be, this little guy. That's going to be really whatever the omega 1, right? So I'm going to write this up here, just that omega 1, and then it would be crossed into R from P to A. So if you did the VREL term, right, if you only attached omega to this guy, right, to the bar, and it's not rotating with omega 1, then this would be your VREL term.
Okay, yeah, that makes sense. But now, so if we were going to solve using this equation that you gave us, this VP equation was relative to A, now we'd have to find the point velocity of A using omega 2, right?
Correct.
So then we would have to basically just switch this here, let me annotate real quick. So it would be VA, VA equal to what I put down. It's going to be it's going to be VO, and then that's going to be added to omega 2, and that's going to be crossed with R A relative to O.
That's correct.
And then is there going to be a V relative term to that?
What do you think?
I think that it's just tricky because this it's just attached to like VO on that same axis from O to A. So I'm guessing it's not going to have a relative velocity.
Yeah, you're correct. So a couple ways I'll think of it are, so this bar is really one piece. Do you see that, right? That's one piece. So it's not like this can rotate or anything. So you'll sometimes hear me say, it's like 2 points on the same rigid body. So you really aren't going to have relative, the VREL type of term for it. Okay? Or if I stop the omega 2, right, then is A still kind of moving with me sitting there, right? And it's really not. Okay.
Okay. So this just crosses out to 0 too.
Yeah.
All right. Cool.
So Megan asked, could you just have the big omega be omega 1? And that's actually something you can never do, Megan, because if it's like an outer one, and so what I mean there is, let me go to the next. So if it's one like this, right, where we did the ASDD, right, then I can't have this guy go pitching around and say that's all it's doing, because I'm still going to feel the planetary as well. So I can never really have the big omega just be what's farthest out. You know what I mean? It's got to always include everything before it too. Do you understand what I mean, like by before it, Megan? Okay, so the outer always includes the inner. All right. I can't remember. Were there other questions about this first one? Yeah, so Moulet's asking, should we find the velocity p in the B one first, then transform it into the next kind of the other B one so that it has beta? Yeah, I mean, those are going to be your differences, right, between the beta and the, between the big B and the little b is going to have there. So yeah, because you can solve like this velocity part here, right, of p is actually always going to be in the x double prime. Does everybody see what I said? So think about that for a second. I should have asked you. So everybody see if you agree with me that the velocity of point P, kind of relative to this point A, right, is always going to be in a, right, that component, you're going to have some that's at least always in the x double prime. That's just due to the omega 1 term. Okay. So yeah, I would transform it into the B, because I can't remember what we asked you to find it in. Let me see. Write a short O just for every angle beta. And yeah, that'll work as well, Moulet. But you can find it in any one you want, right? Because the magnitude of it's going to be the same no matter what. Okay, and then there were a couple problems with, right? So Jason's asking, and I think so as Will, right? You guys were both asking about the last one? Okay, so for this one, with the Coriolis, right? So in here, we've asked you to put the, basically we've set the axis here, right? So we've got your axis that's going on here. So if you want to figure out the, right, the Coriolis part, I'm just going back to look to see if we had asked you anything there, and it looks like we didn't. So really, you're going to have to figure out, what is your V of C, your total VC rel term, right? So in this case, which is the same as the R dot one. All right, so we've asked you to put the capital omega, right? So this is one where we're trying to get you practice with all the different ones. This one's just going to be with the omega 1, right? Didn't we? Yeah. Okay, so what you really have to do is start thinking about what that V, C rel, or the R dot is going to be, right? So that's the one for the first. Right? And then, and I think we gave you the answer for that too, right? The R dot, which is the minus 1.8 plus 7. All right, let me see if we've got. Let me just double check, because maybe we did give you the wrong. Okay, sorry. Different numbers. Did we? Oh, okay. So that's not the Coriolis. That's just your rel term, right? The R double dot. So that's just a rel term. Okay, so if you're looking for that one, remember again, we're just kind of, we're now hanging out at right here, right, and then we're looking up this way to see what's happening with that R double dot one. Okay, so what that term is talking about is all the different ones where if I'm again just kind of looking up like this, what is and I'm only rotating with the omega 1, right? So I'm only spinning around this way, but I'm not riding along with this one. Okay, so if I'm doing those, right, then there's going to be a couple of things. And I think I know maybe where that's going to be. a little confusing there. And so what's going to happen there is that you've got well, what two types for C would you have just looking at it to start out with? What types of physical things would be there, do you think? Yeah, so we got a normal, right, because of that would be going into here because of how this guy's rotating around, right? And that's going to go back this way. Does everybody see that? That the normal acceleration of C relative to this frame here, me looking, is really just going to be down towards B, towards where it's rotating. Okay, and then it's also going to be going, and that's going to be like the 1 times r squared. Then I'm going to have some sort of a tangential one going this way. Right. Then what else might I have? The rel, right, that Jason was saying, which is going to be going in this way, and that's going to be what this term is. Okay. But we have one more thing. Anyone want to take a guess what that is? Well, that'd be kind of like, that's a nice guess, Danny, because we did that a couple times to you, right? But in this case, that's going to be the normal one, and that really came into play with this normal where it's like an omega, sorry, it would be like a 7 squared times r. No, because the omega 1 doesn't come into the rel terms, Logan, right? Because the rel term means it's kind of like omega 1's not doing anything at all. Guys are coming up with good possibilities. Anybody else got a thought? Why don't you just tell us, Dr. Yourself? You actually, yeah, Jason's got it. It's actually, you have a Coriolis term here that goes in, okay? Because you've got this 7, right? So this thing's rotating like this, right? Your velocity is going like that, u2, and then a second later, it's going like that. So for this case, even though omega 1's, you know, we've said that one's, we're looking at it from that frame, then we still have this Coriolis term, and this is going to be, and this is included in the A-rel. So within that A-rel term, there's going to be just everything like, there is everything like you guys said. So you're going to have an AC rel, and I'm just going to call that a normal one, right? So that's a normal one, which is going to be with this 7, right, times that 1 foot, 7 squared. And then you're going to have an AC rel that's going to be a tangential. And then you're going to have a U dot for that thing sliding up. And that's, of course, let me see. I should have done that. A U dot. And then you're also going to have a 2 times the omega 2 crossed into the U term. Okay, and that one's tricky. Okay, and there was, you know, a lot of times on those homeworks, right, we give you those additional homeworks along with the solutions that we post, and a lot of times those are ones to try to help you figure ones like this out. So one of those is a little similar to this one where we had the slider. Okay, so I'm going to head out. I will process this with the video, and it does take it a little while to go because I have to download the file and then it goes through and processes things. So I'll probably get this posted in about a half an hour or so. Any last minute questions? I think we've actually talked about just all of them, haven't we? At least a little bit. Yeah, you're welcome. This is the first time I think everything, as long as we get the video going, right, then it'll be the first time we've had everything work right. All right, you're welcome, guys. Have a good night.